Hello everybody and welcome to a video on what is casting. Today we're going to be talking about what up and down casting is in C++ and the different kinds of casts that you can do, which are static, dynamic, and reinterpret cast, the scariest of them all. So let us first start by refreshing on what casting is. And in C++, when you're talking about casting, what you're saying is you want to take something of a certain data type and convert it to another data type. So for example, say that you have a float. And this float is a number that has a decimal point associated to it, right? And you want to convert this into an integer. Now, an integer contains whole numbers. So you can always just create an integer variable, say int x and float y, and let's say that you're storing in y that 3.4f. And if you go and say x is equal to y, what you're doing there is known actually as coercion. Let me go ahead and write that out. So that's coercion. And what coercion is, it's sort of like behind the scenes casting. It's actually what's known as implicit conversion. And so you're taking a number that of course can't fit into an integer, and it just drops the remainder of the numbers on the right side of decimal, right? So if you even had 3.9 and you were putting that in an integer, it just completely drops it off. So it doesn't do any rounding, it just drops it off, what is known as a floor function. So that's your casting as you know it, or at least that's coercion, which is behind the scenes casting. Of course, this is good and bad because it's good because, well, you know, if you don't do this, then what's going to happen? What's going to be stored in an integer, right? It's bad because if you're not aware that this is happening, it can bring some problems, right? Because you might be thinking that 3.4 is actually being stored in X when it's just 3 anymore. So even now, if I go in later on in my code and I put that integer into a float, sure, it's being converted into a float, but all I'm converting is a 3. So I am going to still just have a 3. So I lost accuracy, right? So that's casting in a nutshell. And the way that you do casting as an explicit conversion is by using your static cast in C++. So the syntax for that is to write the word static cast and then go ahead and put what you're casting to. So let's say you're casting an integer to you're casting a float to an integer, as we were doing above. And what you would do here is put in here whatever it is you want to cast. So let's say you put the float in there. So let's say we put the y, because you know y is the float. And then you assign this to whatever you want to store the integer. So that's x, right? So we have an integer x that we're storing here. And what is happening now is you're being explicit about it. You're not letting the compiler handle this. You're not letting anything happen behind the scenes. You're saying, I want to cast this, and I am well aware that it's being cast. And that's a good thing because you want to make sure that there's no behind the scenes things that you may not be aware of that could cause issues, right? Here you're being very explicit and saying, I am converting this float value into an integer. And how do I know it's an integer? It's because I'm putting it here. Now, be careful. If here you go and put something like, let's say a double, you wanted to convert this float into a double, but over here, this is actually a integer, then you're casting float to double, and then there's coercion happening to integer. So that's actually worse. So definitely don't do that kind of thing, but be aware that that could happen. So you don't have to necessarily cast to built-in data types. If you have an object, you can also do casting, and that's where all of the other types of casting are going to come in. So while you can try to cast one object to another object, the compiler is going to have a hard time understanding what you're trying to do, right? So suppose you have a class A, and this class A that you have is contains some data in it. Let's just put an integer in there. And then you have a class B that also happens to contain an integer. Okay? And you say, well, I would like to cast A to class B, right? So, you know, you might be compelled to say, here's an object of A, here's an object of B. You can add some things in there, so you can see something like A dot, I call that x, yeah, a dot x gets 55 or whatever. And now I would like to say B is going to now get A. I'm going to cast the object. So you could try to do something like this. Or actually other way around. I want to cast to B the object from A. However, the compiler is confused about this because it's like, yeah, I mean, like, this might make sense to you because, like, okay, you have a, you have a variable x in both, you have an integer variable as one of your fields in the class. So, like, it kind of makes sense to you that, well, whatever is in x, I want to put in y. And so you might be compelled to say, okay, this is okay to do, but the compiler is going to yell at you. Furthermore, if you try to do this with pointers, so let's go ahead and make a dynamic. So let's say a star here gets a new a, and then we can say a dot x gets 55, and we make this a pointer. This is a little bit more viable because it's pointers, but you're still going to get a compiler that's not very happy about this. Something like that. And the reason being because, well, they're completely different types. And so the compiler still doesn't know how to do the conversion. So you typically would not cast between classes like that are completely different. You can use a copy constructor, or you can overload some operators to do this kind of thing, but it's not going to work right off the bat. Okay? So let me tell you some examples where you might actually want to cast a class to another class. And so this is what's going to come into what is known as up and down casting. So up and down casting has to do when you're casting a parent to a child or a child to a parent. Now, when we're talking about parents and child, we are talking about inheritance. So let's go ahead and change our example to say that B is actually a class that is inheriting from A. So now we have actually A being the parent of B. Okay? So now things can get more interesting, because now I can actually make objects of class B be pointed by an object of class, a pointer of class A. So let me give you an example of that. So right here, when I make our B here, I could, in theory, make a well, here, let's do the following. Let's make B so we have a B pointer that is pointing actually to an object of class A. So here we have really an object of class A, but it's being held by a pointer of class B. Okay? And so in this case, we're fooling the compiler, and we talked about this the other day in terms of how we use virtuals to kind of solve these issues with fooling the compiler, to avoid issues with the destructors and whatnot, and constructors. And that's kind of what we're doing here, right? We're trying to fool the compiler. But why would we want to do that? Well, you may want to store you may have a base class for a big project that is sort of shared amongst different subclasses. And so, for example, if you're building a game, you might say, okay, here's my game, and I am going to call this class entity. And then from there, I'm going to have different classes for players, for obstacles, for NPCs, for other things related to the game, weapons or whatever, if you're like an FPS shooter or something. But they all have a base class of entity. And the reason you want to do that is because now you can make a two-dimensional grid, or whatever dimension you want, one-dimensional, that is made up of a lot of little pointers of the superclass. So in this case, of like the entity class, okay? And so these little pointers, they can hold any pointer of entity, but they can also hold any pointer of any derived classes from entity. So in that case, it could be your player class or your obstacle class, and so they can live there. And you can move them around on the pointers based on where you want to store them. And so it's this idea of making an array of base class pointers that then point to classes of that are derived from that. And you're able to have that flexibility because, remember, in C++, when you have an array, it's a homogeneous data type, which means you can only hold one type. And you are really holding one type, which is entity pointers. The cool thing about it here is that because they're entity pointers and you're doing this casting, you're able to actually hold pointers that are of derived classes from entity. So you're sort of finding a loophole around the limitation that you get usually with the compiler, that you only hold one type. So you have that flexibility, they have that polymorphism, which means multiple shapes, multiple forms. Okay? So before we go a little further ahead, let's go ahead and give you an actual example of up and down casting. So I'm going to change this back to being a and I'm going to make a pointer of B. Okay, and so right now, and actually, you know what? Let's make one object of B here as well. Okay, and then we maybe assign something to the Y of that. Okay, so here we have two objects, and then we're going to make two more pointers. We're just going to call it A pointer, so AP maybe, and then B pointer. And now I am going to go ahead and use a different kind of cast. I'm going to be using dynamic cast. So that's the second one of the list up here. Okay, so what is the difference between dynamic cast and static cast? The difference between dynamic cast and static cast is that dynamic cast is more flexible at allowing you to cast something from one type to another, and you typically are going to be using it strictly on pointers. And there is an additional check that happens at runtime that will allow you to do the cast if it's valid. So here's what you could end up happening when you're doing static cast with pointers. Static cast is going to limit you in what you can and cannot cast. And if you have a pointer that is pointing to a derived object, so for example, I have my BP pointer, and forget about how I got it to do this, but let's just say that this BP pointer is actually pointing to an object of class, or actually, here, yeah, this one's better. Let's say that we have an object here of the A pointer that is pointing to an object of B, okay? So in this case, we have somehow made a pointer of the base class point to the derived class, okay? So we have our entity pointer pointing to a player, or in this case, we have a pointer pointing to a B, and B is derived from A. Now, I want you to think about the dangers of this line of code. If this is really a B object, as it is in this case, B has extra variables that A doesn't have, right? And so we have to be very careful about that, because you don't want to access things that are actually yours. So while we can guarantee that anything in B is also going to be in A because B has everything from A, we can't do the opposite, right? So if down here we went and said, okay, I'm going to somehow make this point to an A, that's really dangerous, because here's the thing. B has everything from A, so sure, I could go and say, and something like cout BP dash X, right? Because that's the X from A. So sure, that's going to be okay, because this is really an A, and all B objects have stuff from A. What's really bad if I try to access what is from the B side, so like the Y, because this is really an A object. So even though the B pointer is holding on to it, it's not actually a B. So there does not exist a Y in this object, right? So if you somehow manage to fool the compiler into storing a child object and a parent pointer, then you run the risk of accessing things that don't exist. So dynamic cast comes to the rescue when you're trying to do that kind of cast, where you're trying to do something in the direction that will potentially put you at risk. And what dynamic cast will do is at runtime, it will attempt to do the casting. And if the casting is valid, so if casting from one type to another is a valid cast, because for example, if you have something that is an A pointer, but in reality it's actually a B, it's just being held in an A pointer, then it's going to be okay with you doing that. So what I'm saying with that is this example. Okay, so now let's think about what's happening here. First, we created a B pointer, and this B pointer was then allocated an actual B object. We know that actually has both the Y and the X because it has both classes in it, because it's derived. Okay, from there, I went ahead and created an A pointer, and I went ahead and made B, the B that we created above, be held by this A pointer. Okay, this right here is what's known as upcasting. Okay, so in this case, we are casting what is essentially a child object or a child pointer to a parent pointer. So we're taking a B and we're converting it to an A. It's just the pointer we're converting. But that's what, I mean, we still have the other B pointer, but we could get rid of it and then, we would lose that pointer, right? We could set it to null or whatever. But the point is that we are doing what is known as upcasting. Okay, so that is upcasting when you're taking an object from a child and you're casting it up to a parent. Okay, so child to parent, that's upcasting. Okay, think of like a family tree, you're going up the family tree. Next, we have the following line of code. We have a B pointer, which is a pointer of a child, and we're going to cast an A pointer. Okay, so we're casting now the other way around. We have this right here, which is an A pointer, which is for parent, and we're casting it to a child pointer. So that is what is known as downcasting. So you're taking something that is currently a parent and making it into a child. Okay? One of these two type of casting is very dangerous, and the other one is actually not dangerous at all. Which one do you think is dangerous? Well, think about it here. When you're going from child to parent, that's not particularly bad. Well, they're actually both dangerous, but not super dangerous. One of them is super dangerous and the one's like slightly dangerous. So when you're casting a child to a parent, it's not particularly dangerous because all you're really doing is you're limiting your access to some of the contents of the class, right? So if we think about what A and B contain, you can think of it this way. A contains an X variable, right? That's your integer X. And then when you inherit B, that is containing everything from A, and it's also containing a Y, right? So if I have here my B, and all of a sudden I say this B is now going to be known, henceforth you shall be known as A. In that case, well, that's okay. It just means that all we can access is going to be what's inside of that, which is just the X. Which means that even though we technically have a Y, we have no access to it because we don't know that it's there. The only downside to this is that if that Y was dynamically allocated and then you call your destructor, then of course you would have a memory leak. We saw that last time that the way you fix that is with a virtual. You make the destructor virtual, and then it actually knows that, hey, this might be pointed by an A, but it's actually a B. So don't forget to call that destructor. So that'll work okay, no problem at all. But it's not particularly dangerous other than that issue. The other story is a lot scarier because if you have something that is pointed with an A and you're now going to make it point to a B, well, if it's a B originally, then that's okay. You're just giving access to things that you had lost because you were holding it in the parent pointer. Great, we have more access to things. That's good. Where it's not good is if this is really an A, and even though it could also be a B that's been put in an A, it could really just be an actual A. And if now this A is being pointed by a B, well then you run into a situation where like this Y doesn't really exist. It's just not part of the code. Like it's not part of the memory. And so if you try to access this, then who knows where you're accessing it. In fact, what ends up happening is in memory, accessing a variable in a class is nothing more than some pointer arithmetics. So it's just going to access invalid space, and you might get a seg fault out of some kind of out of bounds kind of error style, or you just might access garbage, and then that's probably worst, right? So neither of those are good situations. And so when you're doing casting, when you're doing downcasting, when you're doing upcasting, C++ is pretty chill about that because, again, the risks are really small. It's mostly like a memory leak risk, and that's it. But when you're doing the downcasting, C++ is super strict about that and will not let you do it with a static cast. You have to do that with a dynamic cast. Because what the dynamic cast is going to do is it's going to be like, all right, I'm going to let you cast that from parent to child, even though child could have some things that parent doesn't. And if this is really a parent, then all of a sudden it's going to have a crash. But what it's going to do is going to be like, I'm going to let you do that in code, in compile time. And then I'm going to get back to you at runtime. Because at runtime, when you're actually doing the cast, it's going to check if it's a valid cast. It's going to check if like this object that is being held by a parent pointer is really a child object that you can then convert back to child. But if it's actually a parent and you're trying to make a parent into a child and it really is a parent, then it's going to say like, no, that is not legal. You will not pass go. And so instead of doing the casting, what's going to end up happening is you're going to get a null back. So when you're doing a dynamic cast and the dynamic cast fails, instead of giving you the same address of the cast, you're just going to get a null. And let's understand what I mean by address. When you're doing a casting with a pointer, all you're doing is changing the pointer type, but the location in memory stays the same. So the address stays the same. So like, you know, if I have two pointers, like just think about like a simple pointer with an integer. So we have integer A, and then we have integer B. And if I go ahead and say B gets A, you know, all you're doing is you're copying the address, right? And here, in this case, there's no casting, but even if it was casting, you're still just copying the address. The contents don't really change. With dynamic cast, what's going to happen is, if it fails, it's actually going to give you back a null, because then that will actually help you out later. As bad as it sounds, it'll help you out later because you can check if after the cast, the pointer that you expect to contain this brand new child object is actually just containing a null. It means the cast failed, so you can then handle that issue. Or if you don't handle it, then you can just have a null pointer exception and crash. But the point is, you're not going to access weird invalid data. Sometimes it's better to crash than to keep going with wrong information that is going to cause worse issues. Okay, or just waterfall into like a massive issue. So let me actually give you an example. Here, let's modify this example and see how this actually would work. Because if you try to run this piece of code right now, it wouldn't compile. You still need to add in the actual cast in there. So let's move this out of the way. And let's move this out of the way. And I have a little reminder. This is what I like, and I think you saw me paste it earlier. Just remember, upcasting is child to parent. Downcasting is parent to child. And just in my head, I think of a parent as a taller person than a child. So like parent, child. So going down, you're going from parent to child. You're going up, you're going child to parent. Okay? And so in this case, what you do is you write the words dynamic casting here. Put the parent type, which in this case is, the child type, which is B. And then put that in parentheses like that. And there you go. You have done a dynamic cast. If you try to do a static cast there, it probably wouldn't work. For this one, I think you can get away with doing a static cast without issues. Or you can just put nothing, and it'll also work. But if you want to be explicit, you can say static cast. In this case, it's an A. Actually, I should have made that uppercase B, yeah. Notice that I have to put the pointer in there because I'm casting it not to the object type, but to the pointer. I'm making an A pointer, I'm making a B pointer, I'm casting to B pointer, I'm casting to A pointer. I'm not actually changing an object, I'm just changing the pointers. Okay, and that's why I'm also passing it just a pointer in there. All right, so that would be a better way of coding that. And finally, we have reality can be whatever I want type of casting, which is reinterpret casting. Reinterpret casting is really fun. It's my favorite type of casting, and it's actually not C++. It's actually a thing from C that kind of got carried over into C++. Reinterpret casting, you know, I tell people, you know, like everybody I know, I just tell them like I consider that to be like YOLO casting. You know, you only live once casting. Whereas static casting is the safest because it does a lot of checks. Dynamic casting is less safe because it defers some checks to runtime, kind of like virtual style. Reinterpret casting is like, okay, you're trying to do some nasty stuff. I'm just going to look the other way and compile the code. It's going to do the cast and it's going to like it. And it's going to accept it, and it's not going to put if and buts. You want to cast a object into an integer, it's fine by it. It will let you do it. Well, as long as you're dealing with pointers. I think if you're actually casting an actual object, it might give you some issues. But you can actually get around that if you use like the F permissive flag. At that point, you really should not be doing that unless you're just having fun, but not for real code. Okay? So Reinterpret is super cool because it allows you to do a lot of very interesting things. First of all, I mean, you can do your dynamic cast with the Reinterpret cast if you like to live dangerously. But the really cool example that I want to show you and just kind of end the video with, since I believe that's all of the things that I wanted to talk about, yeah, up and down casting, yeah, is this. So suppose that we have a private class. So you've been told all semester longs that when you have a class, and our class, actually let's call this class S for secret, and let's just say it has a private variable int x. Okay? So we have a secret class with a secret variable, and this secret variable is inaccessible to main, right? You could inherit this and it would still be private even if you inherit publicly. You could do all you want, but the point is, in main, if I go ahead and say ss, and here let's initialize it, just cause I could build a constructor, but too much effort right now. So we initialize it, and if I want to see what's in there, so I want to see sx, or if I make a pointer, gets new s. If I want to see what is in here, it's not going to work. It's going to give me an error and say that you're trying to access a private variable, and they are correct. Well, don't let your memes be dreams, and don't let some error stop you from doing nasty code, because you can access that. There's a lot of ways, and a lot of them involve pointer magic. It turns out that one of the things that, without even thinking about Reinterpret, the address location of this int x is going to be the same address as the location of the s, because that's the first variable that appears in that order. So if you wanted to access that, it's just as easy as either casting this pointer into an integer and then just counting it, or you could build a fake class and then just completely cast the entire object. So let us do both of those. In fact, let's start with the overkill example with the fake class. So instead of making a class, just because I don't want to have to write the word public, I'm just going to make a struct. I'm going to call it fs for fake struct. Or sorry, not fake struct, but fake s for fake secret, I guess. And we're just going to put the same ordering of the variables, which we just have one variable. So I'm just going to put it. It doesn't have to be the same name. It could be whatever you want. Reality can be whatever you want, or whatever I want. And then, so now we have this class that we have to know the ordering of the variables. That's the catch with this. But we have a class that matches the exact same ordering of the variables. Okay? So now I am going to go ahead and make a new pointer of the fake s class, and I'm just going to call that fs, lowercase. I guess this one's uppercase, or here we'll just call it, s2 or something. And what I'm going to do now is I'm going to take my pointer of s. And by the way, if this was not a pointer, you could just make a pointer, right, of a variable. So here I guess I'll do both examples. So we'll make one that's not a pointer, so we'll just call this one x. Or we're not x, because we're using x already. I don't want to confuse you. So maybe like a g. So, sg is just a variable. Yeah, there we go. So we made that. So if we wanted a pointer for that, all we got to do is do something like s gs gets address of g, right? So either way, you can get a pointer out of it, whether it's dynamic or not dynamic, as you can see here. So let's go ahead and access for both of these that secret x. Okay, so what I'm going to do with this new variable that I made here is I am going to go ahead and reinterpret cast either of those pointers there, and I will be in business. So reinterpret cast, and then make it into that, which is a fs class pointer. And then I'll put the parentheses in the next line so I don't run out of space there. Or here, actually, I'll just shrink it a little bit. It's not that much left. And in the parentheses, I'm going to go ahead. And by the way, this syntax here, it looks kind of weird, but once you learn templates next week, or 2 weeks from now, it'll make sense. Okay. So yeah, what am I going to put in there? I'm going to put in there whichever one I want to do. So first, let's go ahead and do the let's do the G one. So GS, I put GS in there. That's this one, that I'm pointing to with this pointer here. And now what I have done is I have a pointer to a struct. And this struct is public, and that int x is public. So I can just go ahead as easily and say s2x, and I could change it if I want to, or if I want to see what is in there, I can just cout it and then change it. So I have hacked into the secret variable, just as like that. So look at that. You thought private variables were safe? Well, think again. And again, we could do that with the other one. That one's held with an S pointer, so just make that an S. Same deal. Back in the day, I had an assignment called Crack the Vault, where I had 6 different vaults that were all things like private variables and things like that. And it was a really, really fun assignment. I loved it with a passion. And this was pretty much the purpose of the assignment, was to, one of the vaults was to do this, and it's all about hacking it. And obviously, there's a catch to this, and that's you need to know the ordering of the variables in the class. But using this method, you can basically access any private variable of any class. So that is why when I first taught you classes, I said privates are not there as a security feature. They're more there as an honest man's security to not accidentally do things you're not supposed to do. But by no means is making something into a private variable a secure way of storing information. It is just there to not make mistakes. It's to prevent accidents from happening. It's like imagine that you have like a ditch in your house that's like really deep, and you decide to put a door with a lock, just because in case you accidentally go in there, you don't fall in there. You have to actually remove the lock, which takes time and process. So like that's your sort of buffer, so that even if you're like half asleep at night in your yard, you don't fall into the hole, right? It's not meant to keep people out of the hole, because anybody can just break the lock out, but it's more meant to just prevent you from having accidents or your visitors from having accidents, right? It's not like super cyber secure. People can break the lock if they want to, but that would be intentional, which means that at that point they know what they're doing, or if they don't, then at least they had a warning because they saw a lock there, right? So yeah, okay, that's Reinterpret cast, and the other method that I said is with just a pointer, which you can do too. So like for example, if you have an int pointer here, I can do the Reinterpret cast with this pointer as well, and that'll work too. That pointer asterisk might go after the type, not before it. I've been putting it before it, but I think it goes after. I have to enter it in code. Yeah, it goes after. I don't know why I was putting it before. I'm pretty sure it goes after. I guess it wasn't as obvious when I was just looking at custom data types. With the built-in, it's kind of obvious. Like I wouldn't put it before. So sorry for that. So what I'm saying is like this here should be fs star, I believe. Yeah. Okay. Either way, you would have had a compiler error and figured it out yourselves. Anyways, I wrote static cast. I meant to write Reinterpret cast. Okay. So once you do that with Reinterpret cast, then all you got to put in here is either of the ones you want. So S or SGS. I'll just put S in here. So now S has basically that address. Or sorry, PTR has the address from S. And because of the way that memory works, this is actually again at the same address as where object S lives. If you were to cout the address of this pointer, so if you like make it public and then do like cout S arrow X, you would see that this address is matched in memory. So by casting it to an int, you can just access it by just saying cout PTR. Game, set, and match. Done. So Reinterpret casts are super fun. Not particularly useful unless you're doing weird, nasty things you shouldn't be doing, but I love teaching them, and I thought I'd make a fun video about it. More importantly for you and for your assignment is to understand up and down casting, okay? So from like the meta perspective of programming is that you're going to be casting up when you're trying to store objects into an array of a base class. So like again, you got entities and you want to store under your players, which are a derived class from entities. You store them there, and you do this because you are able to store multiple different types of objects in one array in C++ that has only homogeneous. If you were things like Python, you wouldn't need to go through this effort, but you do for something like C++, and that is how you achieve runtime polymorphism, which is a very cool thing. And so sometimes when you're doing that casting, you're more than likely going to want to use dynamic cast for that. Start with static cast. If it doesn't work, try dynamic. If it doesn't work and you feel dangerous, then you can go and do the reinterpret. Okay? And so that's your up. And your downcasting, you really only want to do downcasting when you're sure that the object that the parent pointer is pointing to is really a child, because you haven't previously casted it up to a parent to be able to do this polymorphism. But you definitely don't want to try to cast something unless you know that. So the next thing you should ask is, how can I actually store that information? Well, there's a lot of different ways, and in the next video when I show you pure virtual functions, I'm going to go ahead and give you an example of that so you can check that out. But for now, the easiest thing to do in short terms of what I'm going to do in a bit is that you're going to be making your base class, your super class, have a string or a function called what am I? And this usually you make as a virtual function, a pure virtual function. And then what you do in the derived classes is you actually fill that function, or you replace it, or you at least fill the variable in with the type that you really are. And so now, because that exists in the parent, you're able to access it at any time to find out what the pointer it really is pointing to. So if this is a little bit weird, don't worry, just check out the next video. And I thank you all for watching. Until next time, stay safe.